Hey everyone. So we're starting chapter 7. I believe this is assignment number 13. Um, Assignment number 13 in chapter 7. And we're solving differential equations today. I think after we get done solving some differential equations, though, I do want to go back and look at things we're supposed to be comfortable with. Okay? So, differential equations. Now, this is made a little more challenging because in the year of the pandemic, we had to actually cut out. I made the videos for, but didn't require you to watch the ones dealing with differentials. And so if you didn't actually watch them, then what you don't know is this thing that we say is dy dx equals 2x. This is not dy dx. It's dy over dx. And what's the distinction? Well, the distinction is I can do that. I know, right? Who knew that that was out there? Well, not you if you didn't get to watch videos 71 and 72 from last semester. So what I need to do now is solve this differential equation. These things are differentials, by the way. Okay, so how do I do that? Well, I need to integrate both sides. So if I integrate over here with respect to y, I'm going to get y. And over here, the antiderivative of 2x is x squared. And don't forget the plus c. Ta-da! There it is. That's all I got. Yes, all right. So, look, some of you are like, but Mr. Kukla, each of these integrals has a constant and they might not be the same. Sure, and then your very next step is going to be to subtract c sub 1. And so then you'll have y equals x squared plus c sub 2 minus c sub 1. And if you define c sub 2 minus c sub 1 as c, then lo and behold, you get that. College Board does not need you to do this. They do need a plus c, but they don't need two c's showing up. Okay? So here we solve the differential equation. Now, isn't that interesting? Because in chapter 6, when we looked at this, I asked you the question, what's the antiderivative? And you would have said x squared plus a constant. So why don't I just use my antiderivatives? Well, the answer to that question is yes, I'm definitely going to use my antiderivative approach. Oh, you're the derivative of x squared whenever I can. But there are going to be lots of situations where I can't. And that's really what chapter 7 is about. All the different ways to go backwards, all the different types of antiderivatives we could face. And one sort of class of those problems are the ones using differentials. So if we now have something like dy dx equals negative x over y, how do I solve this differential equation? Well, no worries. We're going to multiply both sides by dx, and I'm going to multiply both sides by y. How come? Well, because when I do, these cancel and these cancel, and now I have, because Alexa off, I have y dy equals negative x dx. Okay? How do we go further? Well, we integrate both sides. And over here, I'm going to have y squared over 2. And over here, I'm going to have negative x squared over 2 plus c. You can have the c over here if you want. You can have the c over here if you want. I don't care where you put the c. I just need the c to show up at the right time, which is when you did the integrating. Okay? So, solving the differential equation, well, you know, I'm tempted to add x squared over 2 to both sides. And so now I've got this, which I guess could be x squared plus y squared equals 2c. Oh, look, 2 times a constant. Guess what? That's just going to be another constant. And it turns out here's the equation of a circle. However, what we're doing when we're solving a differential equation is we want this to say, when we're all done, we want it to say y equals. We must have y equals, okay? I don't have y equals here yet. And even though I'm very tempted to move this over here to highlight the fact that this is a circle, in fact, that this differential equation will always make a circle, I need to follow the directions which say y equals. So I'm going to multiply everywhere by 2. Hey, by the way, 2 times a constant is still a constant. And now I'm going to take the square root. Don't forget, though, plus or minus c minus x squared. Okay. Yeah, and in order to get rid of that c, we'd need an initial condition, another point. And we don't have that in this problem. All right. Next, we're given this differential equation. dy dx equals y. So in the last one, I showed you moving all the x stuff to one side and all the y stuff to another side. And I kind of want to do that here as well. But I also want to multiply both sides by dx. So on this side, I have 1 over y dy. And on this side, I have 1 dx. Integrate. Whose derivative is that? This absolute value, by the way, terribly, 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 terribly important in a way that it's never been important before. But yes, you definitely need to have those absolute values, and I'll explain more about that later. The antiderivative of 1 is x, and don't forget the plus c. Okay, so here we are. Again, we're trying to solve the differential equation. We did the separation of variables. By the way, if you don't show separation of variables, you're going to lose something like 6 points. No kidding. This problem shows up on almost every year's AP exam, and the solving differential equation problem is always worth 5 or 6 points. And if you don't show the separation of variables, where you get the x's on one side and the y's on the other, yeah, the reader is informed to stop reading. Just move on. So please make sure you show that separation of variables. Okay, so what do we need to do now? We need to exponentiate. And please notice, I am not exponentiating each piece. I'm exponentiating the whole side of the equation. Yeah, I am. So over here, I'm going to have e to the x plus c. And over here, these are going to cancel, and I'm going to have absolute value of y. All right? Now, I'm going to do some algebra that you aren't going to like, and you will need to do this algebra. So, what is this algebra? Well, look up here. When was it that I added the exponents? Was it when I had a power raised to a power? No, that was multiplying the powers. Was it when I had the bases are the same and I'm multiplying that I add the powers? Why, yes, it was. So what I notice here is when I'm adding 2 plus 3, when I see that adding, I could actually split this expression into 2 pieces. And that's what I'm going to do. I'm going to say this is e to the c times e to the x. Because the bases are the same and I'm multiplying, I could add the exponents. I know, you don't get it. Why would I want to do that? Okay, now, to get rid of these absolute value bars, I'm going to need a plus or minus. Because that could be -2 or +2 in there. I don't know. So we've got to have both possibilities over here. Now, but wait, it gets better. See this? That's a constant. That's just some number. So I'm going to define plus and minus e to the c to be called the letter b. And so now I'm looking at b e to the x. I think I like that. Yeah, good, nice. Look, we were able to solve the differential equation and find this exponential curve. That was interesting. So what was the differential equation that led to uh, an exponential? It was y. This became that. Whereas dy dx equals negative x over y, this turned into a circle. All right, so let's go a little further. So when I see this, oops, y there, x there. I know I'm thinking about the second derivative being 2x. Great, so let's separate some variables. I multiply both sides by dx, doink, doink, and I integrate. I get, on the left-hand side, a dy, and on the right-hand side, on x squared plus c. dx, no, dy, x squared plus c, yes, yes, that's the first time back. Now if I go oh, there it is, now I understand. If I go back again, I have this, and when I integrate here, I'm going to have y, because that's 1y. And over here, x to the third over 3 plus cx plus d. I can go back more than once. That was the point of that problem. And yes, every time I go back, I have to have another constant. Why don't you try this one? Second derivative is sine x. Please find y equals. Okay? Give it a try. Come back when you're done. Hey, welcome back. I hope that went well for you. Let's check. So if I, oh no, if I multiply both sides by dx, doink, doink, now I'm looking at the integral of dy dx. dy equals the integral sine x dx. Okay, so the antiderivative over here is going to be dy dx, and over here over here we're going to have negative cosine x plus c. If I do my separation of variables again and then integrate, I'm going to have y equals negative sine x plus cx plus d. Okie doke. All right, I got one more. Second derivative is equal to negative 2 over x to the third plus cosine x minus e to the minus x. Okay, so, there we go. I want to find out what y equals here. So let's just do that. What's going to happen? I'm going to get dy dx. Oh, that's y. dx, dx, doink, doink. So I've got dy, dx, dy, integral negative 2. And you might want to make that x to the minus 3 plus cosine x minus e to the minus x dx. So on this side, I'm getting dy dx equals, and over here, I have to add 1. If I add 1 to that, it's negative 2. Oh, there's the negative 2. So that's just going back up. So I have x to the minus 2. Whose derivative is this? This is sine's derivative. And the antiderivative here is plus e to the minus x. How did I know? Because if I take the derivative of this, We get e to the minus x times the derivative of the inside, which is minus, and that's that thing there. Don't forget the plus c. If we now do separation of variables a second time and integrate a second time, we get y equals, now here, I add 1 up there, it's got to be negative 1. I don't see a negative here, so I need negative x to the minus 1. That way, when I take the derivative of this and this negative 1 comes down, times that negative makes that positive. Okay, whose derivative is this? This is negative cosine's derivative. Whose derivative is this? It's negative e to the minus x. Because if I take the derivative of this, I get the same thing, and the derivative of the inside with that makes that. Plus cx plus d. All right, so that's solving differential equations, and you really need to know how to do that. It's probably going to be, if you've got 6 free response questions at 9 points each, that's 54 points total, and we're talking about 5 to 6 points for the differential equation. We're talking about 10% of the test, or 10% of the free response points. Being that one type of question. So no, we can't run away from that. Okay, these next problems don't pause the video. I'm going to give you a dy dx and almost immediately start a countdown. You need to tell me what y is equal to. Okay, I'm going to give you dy dx. You're going to tell me what y is equal to. All right, nobody expects you to do these problems with separation of variables. These problems are going to be the types of problems where when you see them, you're supposed to know the antiderivative and just leap to it. For example, this one. Oh, 5, 4, 3, 2, 1. Yeah? Okay, dy dx, 7x to the 6th. 5, 4, 3, 2, 1. X to the 7th plus c. Dy dx equals 24 x to the 5th. Y equals, I guess we're going below. Y equals 5, 4, 3, 2, 1. Well, this is going to go up by a power. And so when that 6 came down, it made 24. There must have been a 4 there. And don't forget the plus c. Dy dx equals negative 1 over x. 5, 4, 3, 2, 1. Well, I hope you had negative ln absolute x. Yeah, now we need ln to be absolute value. Trust me, trust me. Well, why, Mr. Hoopa? Well, can I take the ln of the negative number? No, I can't. So I really want to have that reminder there. And since that does play a role in the differential equation we solved before, yeah, that's when you'll be needing it. And so you should practice it. And there's, oh, don't forget the plus c. Okay, how about this one? Dy dx equals 1 over x squared. Actually, I have 4 over x squared. And you're more than welcome to think about that as 4x to the negative 2nd. Okay, 5, 4, 3, 2, 1. So what does y equal? Well, I had to add 1 there. If I brought down that negative 1, I get that. Not really, not unless there's a negative 4 there. So that when I bring down this negative 1 times negative 4 is positive 4. Don't forget the plus c. Okay, how about this one? Dy dx equals negative 1 over x squared. And I guess we could think of that as negative x to the minus 2. 5, 4, 3, 2, 1. So it's going to be x to the minus 1 plus c. Okay, right? And always check. Bring that down. Subtract 1. Yep, perfect. Okay, how about dy dx equals negative 1 over x squared plus 1. Whose derivative is that? Whose derivative is that? 5, 4, 3, 2, 1. We know that this is y equals cotangent inverse of x. And if we didn't know that, you need to get practicing those things again, please. All right, how about this one? dy dx, 1 over square root of x. And again, you might find it much easier to write that way. Oh my God, why do we waste time with radicals? 5, 4, 3, 2, 1. So I add 1 to that. That makes that. If I take the derivative of this, this comes down. I don't see a 1/2 here, so there must be something present on the original function so that when I take that derivative, there's canceling that makes that 1/2 go away. So I need a 2. Don't forget the plus c, because I forgot it up here. All right, moving on. Speed round. How about dy dx equals, dy dx equals -1 over square root of 1 minus x squared. No, really, I'm going to start the countdown. 5, 4, 3, 2, 1. And you should have y equals negative cosine inverse of x. No, positive cosine inverse of x, and don't forget the plus c. You need to know your derivatives. This may be a time when you really do need to go back to chapters 3 and 4 and make sure you know all those derivatives that you're supposed to know. dy dx equals 1 over x ln of 5. 5, 4, 3, 2, 1. So it may help, though in my experience, not really, to write the problem this way. Whose derivative is this? This is the derivative of log base 5 of x. How do I take the derivative of this? Well, what if we used the change of base formula and had ln of x over ln of 5, and we thought about that as 1 over ln of 5 times ln of x, a constant times this function, and if I want the derivative of that, it's going to be 1 over x times that constant. Oh, look, there it is. And yes, you really do need to know how to take the derivative of logs as well as exponentials as well as inverse straight functions. So let's do another one. How about dy dx equals negative e to the minus x? Y equals 5, 4, 3, 2, 1. E to the minus x, don't forget the plus c, because I think I did again last one. And what if y equals e to the minus x? Oops, sorry. What if dy dx equals e to the minus x? What's y equal then? Go backwards. 5, 4, 3, 2, 1. It's e to the minus x. Now, notice my derivative doesn't have a negative in front. If I take the derivative of this, I get this times the derivative of the inside function. The derivative of the inside is -1, but there's no -1 here. So there must be something present in the original function. So when we take this derivative and that derivative of the inside comes out, it interacts with this minus to give me this plus. Don't forget your plus c. All right, how about dy dx equals cosine x? And again, you can do separation of variables here. You can then integrate both sides. So this is y equals sine x plus c. But the problems we've been looking at here in this third round No, we're really supposed to just know these or be able to do them very, very quickly without needing to go through this separation of variables process. Okay, so how about dy dx equals cosecant cotangent? Okay, 5, 4, 3, 2, 1. Well, I think it's great that many of you said cosecant x plus c. However, I thought the derivative of cosecant was negative cosecant cotangent. And there's no negative there. So what must be present on the original function so that when I take the derivative and that negative shows up, it actually isn't there. And there must be a negative here on the original function. Okay? How about dy dx equals negative secant squared x? Okay? 5, 4, 3, 2, 1. Well, I know this is the derivative of tangent. Negative tangent plus c. Good. And our last row of problems. Dy dx equals 3 to the x ln of 3. Y would equal what? Whose derivative is this? 5, 4, 3, 2, 1. This is the derivative exactly of 3 to the x. I take the derivative of 3 to the x. The derivative of 3 to the x is 3 to the x times the ln of the base. So times ln of 3. What about this one? Dy dx equals 3 to the x. 5, 4, 3, 2, 1. Okay, so y is going to equal 3 to the x. But wait a minute. If I take the derivative of this, the derivative of this is going to be 3 to the x ln of 3. And I don't see an ln of 3 here. So there must be something present on the original function so that when I take the derivative, I don't have an ln of 3 there. So I'm going to say that. How come? Well, because when I do this derivative, when I do the derivative of 3 to the x, I'm going to have 3 to the x ln 3. And this is on top, and this is on the bottom, and they'll cancel, giving me that 3 to the x. If it helps your brain, you could think of it like that. Okay, so I'm just taking the derivative of this, 3 to the x ln 3. The ln of 3 is canceled. Okay, how about 3 to the x ln 3 equals dy dx? What can we do with that one? Whose derivative is this? Well, I think most people are comfortable saying that y is going to equal 3 to the x. And if I take the derivative of this, I'll get 3 to the x ln of 3. Well, there is an ln of 3, but it's on the bottom. And this is on the top. So when I take the derivative of this, I'm going to have an ln of 3 on the top, not an ln of 3 on the bottom. So I think my original function actually needs 2 of them. So that when I take the derivative of this and the ln of 3 shows up, this ln of 3 cancels one of those and still leaves me one on the bottom. Yeah, that was a little thinking, wasn't it? Plus c. Plus c. Don't forget your plus c's. Oh my goodness. Okay, how about this one? How about dy dx equals pi plus x to the pi minus pi to the x? It's such a good problem for you. 5, 4, 3, 2, 1. Okay, so then y equals pi x plus x to the pi plus 1, hold on a second, divided by pi plus 1, and over here, minus pi to the x over ln of pi. So this is a power function. It's like x to the second or x to the third. So I got to add 1 to the power and divide by that new number. You know, if I had x to the third as dy dx, y would be x to the fourth over 4. See how these are the same? See how I have to add 1 when I go backwards? That's what I'm doing here. This is a power function, but this is an exponential function. A number raised to that variable. That's exponential. And we know the antiderivative of this has got to be this, because I don't see an ln of pi here. And that must mean on the original, there must have been something so that when that ln of pi showed up on the top, it got canceled by 1 on the bottom. And yes, don't forget the plus c. Okay, so those are the things you're just supposed to, it's like your multiplication table. It's like someone says to you 42 and you say 6 times 7. It's really just like that. It's not that it couldn't be 2 times 21. It's not that it couldn't be 3 times 14. Those are all good too. But that sort of sense of speed, of mastery over the content, that's what we're looking for here. All right, now these next ones we're going to call by guess. And don't worry on these next few problems if you guessed wrong, because the rest of this chapter is going to be giving us a method to do these problems without guessing. So, but they're sort of, getting us closer to that time when we need to dy dx. Okay, so I'm looking at this saying, whose derivative is this? Well, I think this is the derivative of negative cosine t squared. Why do I think that? Well, I see this inside function, and I see its derivative over here. And I'm thinking, this is someone's derivative. Whose derivative is that? It's negative cosine's derivative. So again, always check. Guess and check. So what's the derivative of negative cosine? The derivative of negative cosine is sine. Leave the inside alone. Come back and take the derivative of the inside. Fabulous. That's exactly what we had there. Don't forget the plus c. So this is a guessing thing right now. So what if we had this one instead? What if we had negative sine x e to the minus e to the cosine x? Here's our dy dx, and I want to know what y equals. Whose derivative is this? Well, I see that inside function, and I see its derivative over here. So I think I'm just looking at e to the cosine x. If I took the derivative of e to the cosine x, I'd have e to the cosine x times the derivative of the inside function. Don't forget your plus c. Okay. Do we need another one by guess? No, I think it just makes people nervous. All right, you can do this one. 6x cosecant squared. Ooh, yeah, there's a negative. 3x squared. Here's dy dx. Okay? So, what is y equal to here? Okay, so I see the derivative of this here. And this goes with that. Whose derivative is negative cosecant squared? Well, let's go tangent. And 3x squared. Okay, so this is my guess, plus c. Is it right? Well, the derivative of cotangent is negative cosecant squared, leave the inside alone, times the derivative of the inside. Hey, there's the negative, there's the 6x, then the cosecant squared, 3x squared. Yeah, it's all there. Don't forget the plus c. Really, don't forget the plus c. Okay. So yeah, you really need to know your derivatives. Don't worry about those last three. We'll take care of that. All right, the last thing I want to do yeah, what do I know if? What do I know if? If f is increasing, what do I know? Well, I know f prime is greater than 0. If f is decreasing, what do I know? I know f prime is less than 0. What if I see that f is concave down? Well, if f is concave down, then I know that f double prime is less than 0. But I also know something else. F double prime represents the slopes on f prime. And so if the slopes on f prime are less than 0, that means the slopes on f prime are negative, which means that f prime is decreasing. So if I know this, that means this, that means this, or if I know this, that means this, which also means that. I have to know when I see this or this or this, I have to know all three of those things, okay? So if f is concave up, will you fill that one in for me? Please fill that one in for me. Okay, so we should know that f double prime is greater than 0, or f prime is increasing. Why? Because the slopes of f prime are positive. If the slopes of f prime are positive, that tells me that f prime is increasing. All right, what if I know that f prime is greater than 0? Okay, if f prime is greater than 0, what does that tell me? Well, I know then that f is increasing. No, I don't know anything about f double prime. I really don't. If f prime is greater than 0, okay, here's an f prime. Here's an f prime greater than 0. So there's an f prime greater than 0. And look, f double prime would be negative. But here's an f prime greater than 0. Oh, look, f double prime is positive. So if I know f prime is greater than 0, the only thing that tells me is about its antiderivative f, that f must be increasing. If f prime is negative, well, then f is decreasing. What about f prime increasing? What do I know if f prime is increasing? Well, if f prime is increasing, that means that f double prime is going to be positive, and when f double prime is positive, we know f is concave up. And likewise, if f prime is decreasing, then f double prime is less than 0, and so f is concave down. All right? And finally, hey, what do we know if f double prime is greater than 0? Well, that means that f is concave up, or f prime is increasing. And likewise, if f double prime is less than 0, we know that f is concave down, or that f prime is decreasing. And that's it for today. All right, well, I hope this was useful for you, and I look forward to seeing you in our next video. Take care, everyone.